Okay, this is going to be section B, what's left of the paper for you to refer to. I'm not going to do question 10, except to just give you a very brief outline of how it's done, so that when you have done it, you can always come back and have a look at this. Well, basically it works like this. You've got two complex numbers, Z1 and Z2. One is in mod arg form, and one is in Cartesian. And it asks you to evaluate Z1, Z2 in both mod arg and Cartesian. So what you do, you get Z1 is 2 cis 150. You're told so. Firstly in mod arg form, and you can work out what Z2 is in mod arg form, which is root 2 cis 135. You do that division. So cis 15 degrees. And that's the mod arg bit done. And then you do something similar. You do them both in Cartesian. You get Z1. Evaluate Z1 as a Cartesian form, and you get minus root 3 plus I. Z2 is already in Cartesian form. You do that division again. Multiply by the complex conjugate of the denominator to do that division. And you get 1 plus root 3 over 2 plus root 3 minus 1 over 2 I. Then what you do is you take these two numbers, these are equal, and you pull out the real parts. The real part of Z1 over Z2 is root 2 cos 15, or 1 plus root 3 over 2. And that gives you cos 15 is 1 plus root 3 over 2 root 2. And you pull out the imaginary part of Z1 over Z2, and that gives you root 2 sine 15 is equal to root 3 minus 1 over 2, which means that sine 15 is root 3 minus 1 over 2 root 2. Which means you can get tan 15 is sine over cos is root 3 minus 1 over root 3 plus 1, which means tan 75 is the reciprocal of that. And then again you rationalize it, and once you've rationalized it you get 2 plus root 3. So that's a very brief overview of how to do that question. Question 11a. So this is integration. From 0 to root 2, this is integration by substitution. So what are we going to do as our substitution? Substitution needs to be x is 2 sine theta. Cos theta will work as well. Reason it's 2 is because when you square it, you're going to get your 4. The reason it's sine is because when you do 1 minus x squared, you're going to get cos. So dx by d theta is equal to 2 cos theta, or dx is equal to 2 cos theta d theta. Whilst we're here, we'll sort the limits out as well. When x is 0, we get 0 equals 2 sine theta, which means theta is 0. That's one of our limits. And when x is root 2, we get root 2 equals 2 sine theta. So sine theta is root 2 over 2, which means theta is pi by 4, not 45 degrees. You've got to work in radians when you're doing calculus. So, putting all that together, you get that the integration is not from 0 to root 2, it's from 0 to pi by 4 of the square root of 4 minus 4 sine squared theta, replacing x, and replacing dx we get times 2 cos theta d theta. From 0 is just using our trig identity, that's 2 times the root of, I'll put an extra step in, times 2 cos theta d theta, which is, put the 2's together, you get 4. 1 minus sine squared is cos squared, square rooted is cos theta times cos theta d theta. So the actual integral that I'm evaluating, 0 to pi by 4 of 4 cos squared theta with respect to theta. And we can't integrate cos squared theta, so I'm going to use the trig identity. Cos 2 theta equals 2 cos squared theta minus 1, which rearranges to cos squared theta is cos 2 theta plus 1 over 2. So my integral becomes 4 lots of cos 2 theta plus 1 over 2 with respect to theta. Or take the numbers out, factors, cos 2 theta plus 1 d theta. Now I'm ready to actually perform the integration. Cos 2 theta integrates to sine 2 theta over 2. 1 integrates to theta, and we're evaluating that from 0 to pi by 4, which is 2 lots of sine 2 theta, so that's sine 2 pi by 4 over 2 plus pi by 4 itself minus sine 0 plus 0 over 2. That's all nothing. So we get 2 times, so we get sine pi by 2 plus pi by 2. Sine pi by 2 is 1 plus pi by 2. That's part A. Part B, find the integral of from 0 to 0.5 of arc sine x. A couple of ways to do this, the way that you're expected to do it is to integrate by parts using u is equal to arc sine x and v is equal to dv by dx is equal to 1, which means that du by dx is equal to 1 over the square root of 1 minus x squared, and v is equal to x. Substituting all that into the integration by parts formula, which is uv minus the integral of v du by dx with respect to x we get that we are integrating from 0 to 0.5. No, we've done that bit of the integration. So the uv is x arc sine x. We've done that bit of the integration, so it has to be evaluated from 0 to 0.5 minus the integral of v du by dx. V du by dx. So those ones x over 1 minus x squared with respect to x. Now, there's a neat little trick you need to spot here. You can do this by substitution, but you should spot that the thing inside the brackets differentiates to a multiple of the thing on the top. If I put a 2 there and a half outside, they're the same. So I've got 1 minus x squared differentiates to 2x. Or, write it out again, I'm going to rewrite that as 2x times 1 minus x squared to the minus a half with respect to x. And now, since, how best to remind you of this, since this differentiates to this, all I have to focus on is what happens to the power. It's the inverse chain rule. So what would that integrate to? Well, it's going to integrate to 1 minus x squared, and then the power is going to go up by 1. The 2x's will cancel. So this thing here now, I've given a lot more space than I need. If, just to check in your head, if that would differentiate to what was in the integral in the first place, it would differentiate to a half of 1 minus x squared to the power of minus a half multiplied by 2x. So what I've forgotten is the 1 over a half. So now if you differentiate that, you get a half, will come down 1 minus x squared to the minus a half multiplied by whatever this differentiates to, which is minus 2x. So in fact there's a minus sign missing as well, which is why we check. These halves will cancel, so I don't need to worry about them because one's divide and one's multiply, and don't forget your limits. Right, let's evaluate this then using my input. Well, actually, let's write it out like this. It's x arc sine x plus the square root of 1 minus x squared evaluated from 0 to 0.5. And what you do is you drop in 0.5, arc sine 0.5 plus the square root of 1 minus 0.5 squared minus 0 arc sine 0, which is going to be 0, plus square root of 1 minus 0 squared, which is going to be 1. So this is a half of. Arc sine of a half is pi by 6. 1 minus a quarter, this is the square root of 3/4. Minus 0 arc sine 0 is 0, so that's gone. 1 minus the square root of 1 is 1. And just tidying that up a little bit, we get pi by 12 plus root 3 over 2 minus 1. This question itself is quite extensive. So lastly, part C, using the substitution t is tan theta, find the value from 0 to pi by 4 of d theta over 3 cos squared theta plus sine squared theta. Question is, can I remember all that to write it down? So I'm going to use the substitution. No, clearly not. Let's do this. Let's clone this page. This is unusual for a multi-part question in that the parts don't really have any relationship to each other. So, part C. Using the substitution t is tan theta to find that value of that integral. So, the first thing is to differentiate dt by d theta is equal to sec squared theta. So dt is equal to sec squared theta d theta. That's not going to be much use to us though, because I'm going to want to replace d theta. So I get d theta is equal to dt over sec squared theta. Well, sec squared in the first place is 1 over cos squared. So that's what I'm going to use to replace d theta. But before I do that, I'm going to deal with the limits. When theta is 0, I need to know what t is. Well, t is tan 0. Tan 0 is 0, so that's one of my limits, doesn't change. When theta is pi by 4, I get t is tan pi by 4. Oh, that's lovely, because that's 1. So now I can look at the integral that I'm supposed to be evaluating, which is the integral from 0 to pi by 4 of d theta over 3 cos squared theta plus sine squared theta. There's no tans in there to easily replace with t. So let's do it like this. Let's replace the limits, 0 to 1. Let's replace d theta with cos squared theta dt. And let's leave the denominator as it is. So there's a neat little trick you can do with questions like this to make everything easy for yourself, which is I'm going to divide top and bottom by cos squared theta. Now to do that doesn't change anything, but what it will do is it'll get rid of this cos squared theta, turn it into 1, brilliant. It'll get rid of that one, it'll turn it into 1, brilliant. And it'll get rid of that and turn it into tan. So by doing that, tan theta is the thing I want to replace everything with. So I'll get an expression that I can rewrite in terms of t. 1 cos squared theta is 1, 3 cos squared over cos squared is 3, and sine squared over cos squared is tan. D theta, dt. So my actual integral is from 0 to 1 over 1 over 3 plus t squared dt. And this integral is of the form the integral of 1 over a plus x squared dx, which is in your formula booklet as 1 over root a. Actually, I think it's written like this in the formula book. I haven't got the formula booklet open today, so you'll have to double check this yourself. But I believe that's 1 over a arctan x over a. So in our example, plus c, I guess. In our example, there won't be a plus c because it's a definite integral. We get 1 over root 3 times arctan x over root 3. Evaluated from 0 to 1, That bit's going to be easy. It's 1 over root 3 arctan 1 over root 3 minus 0, which is 1 over root 3, arctan 1 over root 3 is pi by 6. Which is pi over 6 root 3. Okay, question 12. Question 12 is less intensive, I feel. But did require. There was a couple of approaches, but I'm going to show you the approach they're expecting. Certainly in terms of answering part B. So, part A, f of x is e to the x sine x. Differentiate that using product rule. You get e to the x sine x plus e to the x cos x. Differentiate it again because, although again it's not clear, this says f double dashed of x. So that is e to the x sine x differentiates to the same thing again. E to the x sine x plus e to the x cos x. And e to the x cos x differentiates to e to the x cos x minus e to the x sine x. These bits cancel. And you get 2 e to the x cos x. That's not quite enough. It wants you to realise that, it wants you to use the fact that cos x equals sine x plus 2. So sine x plus pi by 2. That's part A. B, obtain a similar expression for f-4 of x. It should. These things are structured in such a way that the structure is trying to help you. So start with this expression and differentiate that twice to get my f to the 4. So f of 3, so f3 dash of x is 2 e to the x sine x plus pi by 2 plus 2 e to the x cos of x plus pi by 2 is just following the same pattern as before. And f4 of x is equal to 2 e to the x sine x plus pi by 2 plus 2 e to the x cos. It's going to, like I said, follow exactly the same pattern as before. Cos of x plus pi by 2 plus 2 e to the x cos. So this is differentiating the second term now. Minus 2 e to the x sine x plus pi by 2. Those cancel, and we're left with 4 e to the x cos x plus pi by 2. And if we apply the same transformation again, turn it back into sines, we get sine of x plus pi. And that is the key. That step is the key to answering part C. Because in part C, what you're expected to do is reach the conjecture that f differentiated 2n times of x is equal to, well, if you look at f2, you add 2 e to the x sine x plus pi by 2, and then you add 4 e to the x sine x plus pi. Expected to conjecture that you're going to get 2 to the power of n it wasn't added each time, it was multiplied. Because this follows the same law, doesn't it? This is f0. So it's 2 to the 0 there, 2 to the 1 there, 2 squared there, 2 to the n in general. Sine x plus, and then again in the 0th case, no pi is being added. In the second case, so when n is 1, 1 pi over 2 being added, and then in the third case, pi being added. So that is going to, in general, n pi over 2. Once you've got your conjecture, you can prove it using induction. So, firstly, show it holds for n equals 1. You could, that's what the mark scheme says to do. You could start at n equals 0 without any loss of generality. That's not the right phrase. You could start with n equals 0. I tend to think you probably should, but oh well. Mark scheme says to start with 1. So we'll do f, that means f double dashed of x is equal to 2 to the 1 sine x plus pi by 2, as before, in part, what part was it? A. So my proposition is true for n equals 1. Then I'm going to assume true for n equals k, which means that f of 2k of x is equal to 2 to the k sine x plus k pi by 2. And I want to show that f of 2k plus 2 of x is equal to 2 to the k plus 1. So this is the k plus 1th situation sine of x plus k plus 1 pi over 2. And it's almost trivial because it's exactly the same process as what you went through when you were doing part A and part B. Just doing the same differentiation again. So 2k plus 1 of x is to differentiate 2k sine x plus k pi by 2, which is equal to, oh, I've missed the ECXL all the way through here. Missed the sloppy. There's meant to be an e to x there. Hence there. Hence there. Hence there. Because the reason I noticed that, because I knew I was supposed to be doing some product rule, like I was doing in parts A and parts B. But there was only one function that relied on x. So, differentiating that now, 2 to the k is just a number. We get e to the x sine x plus k pi over 2. Let's leave that as a factor. Plus e to the k cos x plus k pi over 2, exactly the same as before. And then we differentiate that again to get f2k plus 2 of x. 2 to the k. And then differentiate that x, e to the x sine x plus k pi over 2 plus e to the x cos x plus k pi over 2. That's differentiating the sine bits, plus e to the x cos x plus k pi over 2 minus e to the x sine x plus k pi over 2. Once again, these cancel, and we're left with 2 to the k times 2 e to the x cos x plus k pi over 2. Taking the 2, I get 2 to the k plus 1, so we're nearly there. E to the x cos x plus k pi over 2. And then applying the same transformation on cos that we applied in the past to turn it into sine. Sine of x plus k pi over 2 plus pi over 2, which is going to be equal to 2 to the k plus 1 e to the x sine x plus k plus 1 pi over 2. Therefore, since P1 holds and P of k implies P of k plus 1, that implies that P of n is true for all n in the natural numbers by a process of mathematical induction. Right, question 13, last one, a mere 14 marks, and it's only 6:01 p.m. So the last little bit, part A. Given that f and its derivative f dashed are continuous for all values in the domain of f, finding the values for a and b. If f is continuous, that merely implies that 2x minus 1 evaluated at x equals 2 is equal to ax squared plus bx minus 5 evaluated at x equals 2. We can be more formal about that, but I don't think there's any need to. So that gives me 3 is equal to 4a plus 2b minus, it's meant to be 5, isn't it? Minus 5, or 8 is equal to 4a plus 2b. If f dashed of x is continuous, f dashed of x is equal to 2 when x is less than or equal to 2, and it's equal to 2ax plus b when x is between 2 and 3. So, if f dashed of x is continuous, that must mean that 2 is equal to 2ax plus b evaluated at x equals 2. So 2 is equal to 4a plus b, and from before I had my equation 8 equals 4a plus 2b. 1, 2, let's do 2 minus 1 to give me 6 is equal to b. 2 is equal to 4a plus 6. 4a is equal to minus 4. A is equal to minus 1. Show that f is a one-to-one function. Show that f is a one-to-one function. The easiest way to do that is to show that f is increasing on x is less than 3. So for x is less than 2, less than or equal to 2, So equals to 2. F dashed of x, we already worked out, is 2, which is greater than 0, which implies f is increasing. And for x between 2 and 3, f dashed of x is equal to, we already worked it out, 2ax plus b. But now I have values for 2ax and b, minus 2 plus x plus 6. It's obviously linear, which is positive over 2 and 3. Hence, f of x is increasing. And if it's increasing, that must mean it is 1-to-1. Because its gradient is always strictly greater than 0. So it can't ever be coming down, getting the same value again. And then part C is find the inverse function of f. So find the inverse, so let's write out what f was again. This time with the value subbed in. 2x minus 1. Yeah, 2x minus 1. Where x is less than or equal to 2. And we've got ax squared plus bx. So that's what? Minus x squared plus 6x plus 5 minus 5. For x between 2 and 3. So we're going to find the inverse. To find the inverse of the first bit, y is 2x minus 1, y plus 1 equals 2x. Y plus 1 over 2 equals x. Swapping the values, x plus 1 over 2 equals y. That's the inverse when x is less than or equal to 2. Doing the other bit, it's a little bit trickier. Minus x squared plus 6x minus 5 equals y. And then rearranging that to get, completing the square, let's write x squared minus 6x plus 5 equals minus y. Let's complete the square, we get x minus 3 squared minus 9 plus 5 equals minus y. X minus 3 squared minus 4 equals minus y. So we get x minus 3 squared is 4 minus y. X minus 3 is the square root of 4 minus y. And we have to think about whether it's the positive or the negative square root we want. Which is a tough one, actually. We'll come back to that in a second. Which means that x is equal to 3 plus or minus the square root of 4 minus y. Or flipping it round, y is equal to 3 plus or minus the square root of 4 minus x. And that's supposed to be true for x between... Ah, no, I've got this wrong as well, haven't I? Got that wrong as well. So this is for when y is less than or equal to 2, which would mean that x plus 1 over 2 is less than or equal to 2, which would mean that x is less than or equal to 3. And this is how you decide which value of whether you want the positive or negative one, because again, y was told at the start has to be between 2 and 3. If it's between 2 and 3, it can't be the positive one because that will be too big. So it must be the negative one. And if y is between 2 and 3, easiest way to do that is to evaluate what x would be. At 2 would be 3 minus 4 minus 3. So if y was 2, we'd get 3 minus the root of 4 minus x. I'm going to have to redo the whole thing now. 4 minus x, that's 1. 1 is 4 minus x. X is 3. Start with 3. 3 minus that, 4 minus x, which should be obvious then, x is 4. So x has to be between 3 and 4. So the final statement of f inverse of x is equal to, when x is less than or equal to 3, it was, what was it here? X plus 1 over 2. And when x is between 3 and 4, it was 3 minus the root of 4 minus x. That was not my best explanation. I concede. I hope that's of some use anyway.